So, hi everyone, I'm Subhadeep. Hope everyone is safe and sound. So, today I will present my paper titled Hardware Implementation of a Fast 3D Anaglyph Image Watermarking Framework for Integration in Consumer Electronic Devices in the Zooming Innovation in Consumer Technologies Conference 2020. Um, what is digital watermarking and what is the goal we are trying to achieve? Basically, it is the process of infusing some additional information that can be an image, text, or can be an audio, which we infuse inside a digital media, which we can extract later based on some unique key to establish the ownership. So, digital watermarking of image can be used for various applications like copyright protection, intellectual property protection, tamper detection, broadcast monitoring, authentication, etc. So, in this image, what I have shown here, you can see that we can create a digitally watermarked content from the digital watermark and the digital media, and then we can share the digitally watermarked content via either physical media like DVD, Blu-ray discs, SD cards, or either we can share it via the internet or in the public broadcasting system. So this is the process of digital watermarking, and this is the basic goal of digital watermarking. So in the next slide, I'll explain that why digital watermarking is a challenging problem. So as you can see that digital watermarking demands two self-contradictory properties. Those are imperceptibility and robustness. And digital watermarking demands both of these properties simultaneously. So the goal of any sophisticated algorithm should be the optimized trade-off between imperceptibility and robustness. So in the Venn diagram, we can see that at the left side, I have kept the robustness, and at the right side, I have kept the imperceptibility. So in between, there is a sweet spot. So any sophisticated algorithm should lie in that common region of imperceptibility and robustness. So we can see that our proposed method falls in the sweet spot between robustness and imperceptibility. So what is the motivation of our proposed algorithm? So you can see that most of the SVD based watermarkings, they suffer from false positive problems. So the false positive problem occurs when the contender can extract his or her watermark from the watermark image, but the catch is that watermark was never infused inside that original post image. So this is the problem of false positive. So, and the second motivation of our approach is that very few methods which are available in literature that deals with 3D Anaglyph images. Yes, the color watermarking image and the grayscale watermarking of images are a very rich topic in image processing, but very few literature we can find where we can see the watermarking scheme for 3D Anaglyph images. And the most of the published methods are only implemented in software simulation tools like MATLAB or Multisim, like that. But none of the previous algorithms implemented those things in hardware for integration in real life consumer electronic devices. So these motivates us to devise a new algorithm or a new framework which can be useful for our consumers. So I go to the next slide. So now, what is an anaglyph image? So anaglyph image is formed by encoding the left view and the right view images using different filters of different chromatic colors, which are typically red and cyan, as red and cyan are chromatically opposite colors. So the anaglyph images reveals its stereoscopic effect when it is observed through a red cyan tinted glass, like what I have depicted here. So as the visual cortex of our brain fuses these images together, so it creates a perception of three-dimensional scene or composition. So here we can see that we have a left eye image and a right eye image, and by fusing them together using linear projection, we can generate the anaglyph 3D image. And when it is viewed through the red cyan glass, we can see the 3D structures and objects. So now the lifting wavelet transform. So this is the first part of our proposed method. So lifting wavelet transform was proposed by Swildens, and it's a second generation wavelet transform. It is faster and requires less memory space. And LWT, by virtue of its properties, it provides a perfect image reconstruction. And therefore, it is worthy of using in consumer-grade electronic devices, where the perceptual signal quality is of the utmost importance. So, in the figure below, in the left figure, I have shown the forward lifting wavelet transform. It consists of mainly three parts. One is divide, and the dual lifting, and the primal lifting. By these three steps, we can get the low frequency and high frequency subcomponents separated out. And after we do all the processings, we can perform the exact same operations like the primal lifting, after that dual lifting, and at last the merge to get the inverse LWT and to get our original reconstructed image. So here I have depicted one example of lifting wavelet transform. In the left image, I can see that after being decomposed by LWT, the image gives us 4 subbands. One is LL, another 3 is LH, HL, and HH. So the LL subband is the approximation, or it is the low frequency component, which contains most of the image's energy. And the LH, HL, and HH component of the image contains the high frequency detail components like the fine textures or the edges, the vertical, horizontal, and diagonal edges contains by LL, LH, and HH component. And also to judge the best watermarking candidate among all the 4 subbands, we have taken an information theoretic approach. So what is that information theoretic approach? So in the right graph, we can see that I have plotted the entropy of all the LWT subbands for 4 different images, and we can see that the LL subband has the highest entropy for all the images. And also, as a matter of fact, we know that if a subband or if an image has a high entropy, then it's a good watermarking candidate, because high entropy always provides us good robustness and very good imperceptibility. So that is why in this context we have chosen to take the LL subband as the watermarking candidate. So the next proposed approach is tensor singular value decomposition. So for a third order anaglyph image, why I am calling it third order? Because it's a 3-dimensional image. So it's a higher order tensor. So for an anaglyph image of size row by column by number of channels, the TSBD decomposition can be expressed like this equation, where N1 is the row, N2 is the column, and N3 is the number of channels available in that anaglyph image. So which lies in the range of 1, 2, and 3. So after the tensor SBD decomposition, we get total 2 orthogonal tensors of the tensor order 3 and 1 singular matrix which is also of tensor order 3, and we have taken the first singular matrix as the watermarking candidate for the same reason, like I have discussed in the case of LWT subbands. Here also the first singular matrix has the highest entropy, which will give us the highest imperceptibility and robustness. That's why we have chosen the first singular value. So this is the pictorial representation of the tensor SVD. Here A is our anaglyph image, and AS is the singular tensors, and U and V are the orthogonal tensors. So and S contains all the singular values of the anaglyph image A. So what is the advantage of singular value decomposition? So it is fast and it's very memory efficient for its tensor applications, and it can process high order tensors like a color RGB or anaglyph image very efficiently. And the first singular values S1, by virtue of its highest entropy, provides a very good imperceptibility and robustness. So the next thing is Arnold's cat map. So Arnold's cat map is a simple discrete chaotic system that stretches and folds the trajectories in phase space. So and also being an area preservative transform, the size of the image before and after encryption remains the same. Therefore, the encryption has no effect on the payload capacity of the watermarking framework. So for an image of dimension d by d, the Arnold's cat map can be expressed like this equation, where P of n and Q of n denotes the pixel locations before encryption, and P of n1 and Q of n1 denotes the pixel locations after encryption. So here I have shown 4 images. The leftmost image is the original image or original watermark image, and the rest 3 images are the Arnold encrypted image after various iterations like 100 ACM iterations, 200 and 300 iterations. So in those images we can see that the encrypted image shares no similarity with the original image. Therefore, we can tell that this encryption is a really good encryption, and the encrypted image and decrypted image is visually entirely different. So this is the block diagram of our proposed encoder. Here we are taking the cover image, like the cover anaglyph image. We are performing lifting wavelet transform on that cover image, and using that information theoretic approach, we are selecting the highest entropy LL band. After that, we are performing tensor SBD on that highest entropy LL band. And similarly, we are taking the watermark. We are based on the user given key, we are encrypting the watermark using the Arnold cat map. And after that, we are using a total insertion based method to insert W encoder into the singular values of the cover image using this equation, S1 prime equal to S1 plus zeta cross W encoder. So after that, we'll get the modified singular matrix, modified fast singular matrix, and we'll combine this modified fast singular matrix along with this modified singular matrix along with the unchanged U and V matrix to perform the inverse tensor SBT, and after that we'll perform the inverse LWT and we'll get the watermarked image. So this watermarked image now we can share via the physical media or the internet or in the public broadcasting systems. So this is the decoding. So decoding process is exactly the opposite of the encoding process. So being a non-blind scheme, our framework requires the original cover Anaglyph image. Our method requires the original cover Anaglyph image along with the watermarked image for performing the decoding. So first we are doing that LWT on the watermarked image as well as the cover image. After that, we are selecting that LL block from both the watermarked image and the cover image. And then we are performing tensor SBT on both the watermarked image and the cover image, and we'll get the modified S1 block and modified S2 block. And then we can extract the W encoded from the singular values using this equation. W encoded equal to S1 prime minus S1 by zeta, which is exactly opposite of the encoding equation. Now, after this operation, we'll get the encrypted watermark WENC, and again we will have to use the user given key which was used to encrypt the watermark image. And if we supply this user given key to the Arnold scat map, it will generate the decrypted image. And after that, based on the quality and visual quality and correlation coefficient of the decrypted watermark, we can establish our ownership of the original image. So this is the crucial part, the hardware implementation. So software-based implementations has many advantages like the flexibility, ease of use, ease of implementation, etc. Where the hardware implementations have edge over the speed, less overall area, power consumption, memory consumption, etc. So keeping those points in mind, we have implemented a low-cost single-based computer, the Raspberry Pi model 3B Plus. So this SBC runs an ARM Cortex 64-bit system on chip at 1.4 gigahertz. And this comes with 1 GB inbuilt RAM. And this SBC draws a maximum current of 980 milliampere. So we can via the experiments we see that the hardware implementation of our proposed framework boasts up to 80 times performance improvement on average over 50 images as compared to our MATLAB implementations. So we can see that this hardware implementation is really effective and it will aid us to implement and integrate our proposed framework in a real-life consumer electronic devices. So I will come to the result analysis now. So this is the imperceptibility analysis. The top row is the original watermark. The top row is the original Anaglyph images, and the bottom row is the original watermark images. Like that. So from the top row and bottom row, like the original Anaglyph image and the watermark Anaglyph image, we can see that both are near identical. We are visually we can see there is no trace of the hidden watermark, and the perceptual quality of both the watermark and the original images are almost the same. So this method is proven to be useful in the imperceptibility analysis. So now I have quantitatively compared our imperceptibility performance with other state-of-the-art methods. Here we can see that the proposed method has the highest PSNR among all other state-of-the-art methods, making it a well-suited candidate for a consumer-grade electronic device. And also, the average PSNR of our proposed scheme is almost 60 decibel, which is far from average. So this is the robustness analysis. Here we compared the correlation coefficient of the proposed method as well as other state-of-the-art methods under different attacks like the histogram equalization, filtering, sharpening, scaling, etc. So here we can see that the projected scheme has the highest CC among all for all the attacks. So in the test of robustness also, the proposed method outperforms all other relevant state-of-the-art methods. So this is the timing comparison of our proposed method with other methods as well as our proposed Raspberry and our MATLAB implementation. So here we can see that for both the embedding time and the extraction time, the proposed methods Raspberry or the Raspberry Pi implementation has the lowest time recorded in comparison to the proposed methods MATLAB implementation or the other state-of-the-art methods implementation. So here the value is so small actually, it's very hard to see, but here lies our proposed methods Raspa implementation values. It's so small that it's hard to see in this bar chart. So this is a time complexity analysis. So for an Anaglyph image of size P cross Q cross R, the proposed method's time complexity is big O of PQR. And also the average embedding time is 11.32 milliseconds and average extraction time is 19.87 milliseconds. So the application of the proposed watermarking scheme in CE devices or services. So I have categorized it in two parts. One is hardware deployment and one is web service deployment. So in hardware deployment, what you can see that the proposed method having a high visual signal quality can be integrated easily in the mobile consumer electronic devices like the handheld 3D cameras, Blu-ray players, DVD players, 3D video game consoles, etc. And it also can be designed to form a batch watermarking device for watermarking of several 3D images simultaneously. This can be really helpful for our industrial consumer electronics consumers. And the second portion is the web service based deployment. So as a part of online consumer service, this method can also be deployed on web, from where the consumers can directly access this service in any device to protect their digital content and to put watermark on their digital content before sharing it in the internet or in the physical media. So these are the applications of the CE devices. So this is the summary. So to conclude, I can say that our method is very simple but effective in terms of imperceptibility and robustness and security. And this proposed framework has a negligible watermark embedding and extraction timings. And the hardware implementation is also performed for effective integration in real-life consumer electronic devices and services. So this is the reference, and that's all I have. So I'm up for any questions. But before that, I would like to address two questions which were raised by the TCP members. So the first question was, can I give an example of such devices, consumer electronic devices, which can be formed using my proposed approach? So to give an example of such consumer electronic devices, as I stated earlier, for industrial consumers, our proposed framework can also be designed for a batch watermarking device, where the consumer needs to watermark a lot of images sequentially one after another, and this has to be done in real time and very fast. So this is one application, and the second option was the discussion of time complexity. So as I discussed earlier, we use the LWT and the SBT. Both are very fast and memory and time efficient. And for a P by Q by R Anaglyph image, the big O complexity of our proposed framework is big O of P, Q, and R. So thank you all once again. I am up for questions.